Thank you for the invite from MicroLED. And I'd like to talk today particularly about something that was brought up earlier, which is how to reduce chip costs. And the way to do that is to bring the size down. So I'll be talking a lot about chips in the 1 to 10 micron range that we've been working on, along with my collaborators at UC Santa Barbara, where we have over 20 people working on MicroLEDs, especially Professor Nakamura, Speck, and Mishra. Next is supposed to work. Maybe point it here. Oh, that's the right place to point it. Okay, anyways, for the brief outline, I'll, of course, go over a little bit about why we're focused on MicroLEDs, but particularly talk about some of the projection applications, talk about some of the real details, what's helped improve chip technology to what we believe is efficiencies sufficient for things like heads-up displays that we just heard about, and some of the other things. I'll talk a little bit about some of the V-pits we've used to lower the VF, and then even talk about what I consider to be a new, possibly complementary application for MicroLEDs, and that's also to use them as communication devices. And we've showed that you can get very high modulation bandwidths as you reduce the size, and this could be another market that could be used, particularly as we want to go to very high bandwidth and very high, what I would call inter-chip communications for AI, in particular, where they don't want to go with the expensive lasers. And there's I think there's now 4 startup companies that are now working on MicroLEDs for high-speed communication for inter-chip communications. So these two markets, I think, will start to emerge here in the next few years. You know, it's always a long technology, especially in display, as we've seen OLEDs, as Continental pointed out back in 2006, basically took another 12 years to really start to get to mass production. Hopefully it won't take that long for MicroLEDs because we've already been working on it for 10 years. But it will take some more time, I think, to realize the advantages of MicroLEDs and find the right product fits. One of those, I think, really is augmented reality, which can really use the brightness. And another one that I'll be talking about that you're probably not as aware about is using it in the data communication centers as a communication device. So let's first look at the strengths of MicroLED, because that's really where we should have done, and what we should do going forward is really focus on where we can differentiate ourselves with respect to other display technologies. And what really stands out to me is that OLEDs have a limited in brightness. Actually, they're up to about 2,000 candela per meter squared now. And where demonstrations are now in the MicroLEDs is in the millions. So Vuzix demonstrated at Display Week, 4 million nits. So we definitely have the brightness advantage, and we have to take advantage of that because we have a huge cost disadvantage with OLED right now, about a factor of 3, we've heard. While we can reduce this tremendously by reducing the chip size, because those cost analyses were done when the chip was roughly about 20 microns to 10 microns. So taking that down to 1 micron, the costs actually go as the area squared. So we can maybe even get a 10-fold or more reduction by reducing the chip size down to 1 micron. And then you just increase the spacing so you have a lot of free space to use. And so we really need to focus on the brightness, but also the efficiency. We have 90% lower power consumption for LCD, so I really would like to dig down and understand why Continental was saying power consumption was worse with MicroLEDs. It must be in the driver and how they're driving it, because as I'll show you, the efficiencies of MicroLEDs are now vastly superior to OLED at all the colors. So what material system? I think we all know that for the blue and the green, it makes sense to use gallium nitride, but the talk after mine as well, researchers from KAUST will also point out that red also looks like you can now do it with the indium gallium nitride material system. So as you put more indium in, we can shift from blue to green all the way into the red. We just have to solve a lot of basic material science problems along the way, and we're getting there. And I'll talk about some of that work, and they'll talk about their work as well. So I think we'll be able to do all 3 colors here with one material system. So the first problem we had to solve is, and we're still solving, is how to keep the efficiency as you reduce the chip size.